This is the first of my series of videos concerning real analysis with an introduction to logic and proofs. I like to start all my videos with an introduction slide that summarizes everything that is in this video. And I do this for two reasons. One, when I see everything on one slide, it makes me feel like the task at hand is manageable because after all, it is only on one slide. Of course, then I kind of cram the slide full of information. But anyway, and the second reason is this is often the start. If I had to make a cheat sheet, this would be the start of my cheat sheet. As I went along, I'd probably get to know truth tables and I'd probably take it out. So there'd be some things after a while with enough practice would be obvious. But this is the start of what I would say is my summary and my cheat sheet. In this video, we will cover the first four topics: logical statements and connectors, logical implication, truth table, and tautologies. In part 2, a separate video, we'll cover quantifiers and negation of quantifiers. Each video has a number of examples. At the end of each are 2 to 3 review problems for you to do. We are going to start with an introduction to logical statements and connectors. So a statement in logic is a declarative sentence that can be classified as true or false. It's not important that we know if the statement is true or false, but that we know that it can be classified as such, and we will do some examples in a minute. Once we have statements, we can actually combine statements to make kind of bigger logical statements. So we do that by using these connectors like negation. So we can have not of a statement, or we can do conjunction or an and, which is notated with this kind of hat symbol. We can do a disjunction or an or, notated with a kind of a V. And then we can do a conditional, which is an if-then, also sometimes notated with this implication arrow. Here is our first example. We want to know which of these are statements. And remember, to be a statement, a logical statement, it needs to be a declarative sentence that can be classified as true or false. So again, it doesn't need to be true, but it's something that we can classify as true or false. You can pause the video and take a moment to figure out which of these are statements. Here are the solutions. 2 plus 2 equals 4 is a statement. We can evaluate it, and it is, in fact, a true statement. Every continuous function is differentiable is a statement, and we can evaluate it as true or false. X squared minus 5x plus 6 equals 0 is not a statement, because unless we know what the value of x is, we cannot evaluate it as true or false. Every even number is greater than 2. Every even number greater than 2 is the sum of 2 primes, is a statement, and possibly true. If x is a real number, then x squared is greater than 0. This is also a statement, and it is true. This sentence is false, is actually a paradox, and we cannot evaluate it as true or false, so it is not a statement. Next, we want to look at our connectors, our negation, our conjunction, disjunction, and conditional. And I will look at this conditional, the logical implication, also, conditional also called implication. If P, then Q. So P is called the antecedent, and Q is called the consequent. So we should talk about the truth of this logical implication. And for that, I am going to use the example, if I am elected mayor, I will clean the streets. We will look at this as the implication P will stand for I am elected mayor, and Q will stand for I will clean the streets, or maybe it should be I have cleaned the streets, since we have to be able to know if it's true or false. So this is kind of a little bit of a loose example, because instead I'm going to say I will clean the streets, because I'm going to say, is this statement true or false? And I'm going to think of this as a campaign promise. I promised you that if I'm elected mayor, I will clean the streets. Now you want to determine whether or not you consider this campaign promise a true statement, or if you want to consider it a lie. So we're going to look at P implies Q. So if P is true, I am elected mayor, and Q is also true, then we would consider the statement, if I'm elected mayor and I will clean the streets. If I was elected mayor and I also clean the streets, you would say, oh, my campaign promise, I made a true statement to you. I did not lie to you. But if I am elected mayor and it turns out I do not clean the streets, in other words, Q is false, you would say I lied to you in that campaign promise. So P implies Q when P is true, or the antecedent is true and the consequent is false, we say that the implication is false. Now, what happens if I am not elected mayor? Those are our next two cases. Well, if I'm not elected mayor and I go ahead and clean the streets anyway, you wouldn't say that I lied to you when I was campaigning. So you would still say I'm a truthful person. And then if I am not elected mayor and I say, well, I'm not going to clean the streets for you, you'd still say I hadn't lied to you. So that's a true statement. So the implication is only false is if the antecedent is true and the consequent is false. So that's the only case that we would say the implication is false. We can go ahead and look at the rest of the truth table. The not P is essentially just the opposite of what P is. So if P is true, then not P is false. If P is false, then not P is true. P and Q is true only when both P and Q are true. So when one of them is false, then the whole statement is false. P or Q, on the other hand, as long as either P or Q, or maybe both, are true, so that's these first three, then P or Q is considered true. If they're both false, then it's false. We talked about the implication. We could look at Q implies P. So as long as Q, the antecedent, is false, then our implication is true. And it's only false if Q ends up true and P is false. So this is also true if the antecedent is true and the consequence is false. So that's the only case here. We can come up with then more complicated compound statements where we look at P implies Q and Q implies P. So we want to know when both are true. It's true in the first line. Here, only one is true, so it's false, and it's true on the last line. We can, and also this P implies Q and Q implies P is sometimes written as P if and only if Q with this back and forth arrow. We can look at not P implies, not Q implies not P. Well, we have not P here. I didn't write out not Q, so we'll have to imagine it. But not P, the implication is only false when the antecedent is true and the consequent is false. So let's look at when not P is true. That's these two cases. And then the consequent is false. So that would be not Q. So that would be the opposite of Q. So this line, I'm over here, would be false. Everything else would be true. And then we also have P and Q implies Q. So you can go through this. P and Q implies Q. So it's only, this implication is false only when the antecedent is true. It's only true on the top. And the consequence is false. So when this is true, the consequence Q is also true. So it's true all the time. There are other ways of saying the if-then. So if P then Q, it can take the form of P implies Q, as we kind of did in this truth table here. Two other ways that are similar is to say Q provided that P, or Q whenever P. So the idea is this is saying, let's just take Q whenever P. So in other words, if the implication is a true statement, that means whenever P happens, Q is going to follow. In other words, Q whenever P. So in other words, if P happens, then you know Q will happen. That's kind of the same thing here. If you know that P has happened, then Q will happen. That's what Q provided, that P. Two more ways of saying this. P only if Q. In other words, P only happens if it's always followed by Q. Again, it's the same thing as P implies Q. Or P is sufficient for Q. So P is sufficient reason for us to believe that Q has followed. The other two ways of saying this is that we'll look at is Q if P. So if P, then Q. It's sort of the same way. And then last one, Q is a necessary condition for P. In other words, if P happens, then Q is necessary. So these two are kind of two special ones that you should pay a special attention to. It's actually easy to confuse, but if you kind of keep saying it to yourself, you'll get used to it. So P implies Q, these two statements here, is equivalent to saying that P is sufficient for Q. In other words, P is sufficient conditions to cause Q. So that's how you want to think of that. And Q is a necessary condition for P. So if P happens, Q necessarily happens. I'll write that on the next slide. So here I've written those two alternate ways of thinking of P implies Q. So P is sufficient for Q. I think of this as P, knowing P has occurred is sufficient for us to believe that Q has occurred. So knowing P is sufficient for us to believe in Q. Here, Q is a necessary condition for P. That kind of means that if we know Q has occurred, then we know necessarily that P has occurred, because whenever P occurs, Q follows. So Q means necessarily P has also occurred. And P is sufficient for us to know that Q has occurred. So this is a sufficient condition versus a necessary condition. So that's something that you want to be very clear on. Here's our next example. We want to identify the antecedent and the consequence of these three implication statements. So you want to take a moment, pause the video, and give it a try. So the first statement, if n is an integer, then 2n is an even integer. So this one's a fairly straightforward. P, the antecedent, is n is an integer, and Q, the consequence, is 2n is an even integer. So I have the antecedent circled in blue, the consequence circled in green. This next one is kind of interesting. So the car will not run whenever you run out of gas. In this case, you run out of gas is the antecedent, and the car will not run is the consequent, because it is. If you run out of gas, then the car will not run. If we had done this incorrectly, so this is wrong, but if we had labeled this, the car will not run as the antecedent and you run out of gas as the consequent, then our implication would be if the car will not run, then you're out of gas. But that's not really the same thing as what this is saying, because in fact it's talking about what happens when you run out of gas. This is not about what happens or what we can conclude when your car will not run. Also, this is a false statement. But just to write this out, again, this argument or identification of antecedent and consequence is incorrect, because the statement here, the car will not run whenever you run out of gas, is about what will happen if you run out of gas. So the if you run out of gas is our antecedent. So this next example, continuity is a necessary condition for differentiability, is interesting because it'll give us a chance to look at necessary versus sufficient, because the statement is about necessary. Let's just take a look at our two choices. We can either have continuity as P, our antecedent, and differentiability as Q, our consequent, or we could do it the other way around, where continuity is Q, our consequent, and differentiability is P, our antecedent. So P implies Q in this way would be saying that continuity implies differentiability. And if P is differentiability, so P implies Q would be differentiable implies continuous. So we want to know of these two statements, which one is what this English statement, continuity is a necessary condition for differentiability, which one of these two reflects the statement here. So continuity being necessary means that if it's differentiable, you know that it's continuous. So I think it's this one here, P implies Q. So differentiable is going to be the antecedent, and continuity is going to be the consequent. And the reason is that it's not this one is continuity may be a necessary condition, but it may not be sufficient, and that's what this would be implying, that continuity is sufficient to guarantee differentiability, but it may not be. Continuous may just be one of the conditions necessary for differentiability. So we're not trying to say in this statement that continuity is sufficient. We're trying to say that continuity is necessary, and that is why I went with P is differentiable, the antecedent, and Q is continuous, the consequent. So the next set of ideas we need to know are tautologies and also logically equivalent. So let's look at the truth table again. When two different expressions, so here I have not P and Q, and not P or not Q. I can see their truth table evaluations are the same. In other words, when P and Q are both true, both of these expressions are false. And all down the table, they have the same evaluation. So when they're both false, these are both true. So that means that these two are logically equivalent. And what that means is to be logically equivalent, whenever you see not P and Q, you can replace this compound statement with not P or not Q. These are logically equivalent. And also this one is an important logical equivalence because it tells you kind of how to distribute this negation. So if you have a negation outside the parentheses, the P and Q, then to distribute, you distribute the not P and you distribute to not Q, but then you have to flip the and to become an or. So that's logically equivalent. Here's another logical equivalence, which is also very important. The negation of P implies Q is logically equivalent to P and not Q. So you can just look. So in other words, to negate the implication P implies Q, how do you get the exact kind of opposite of P implies Q? Or then what you end up doing is you say, well, that only happens when P is true, but Q is not true. So those two things are logically equivalent. So whenever you want to negate an implication, you can replace it with P and not Q. Again, how do you negate an implication? Well, the implication is always true except when P is true and Q is false. So when P is true and Q is false. Last, a tautology is if you look at not P and Q over here, and not P or Q, and you do the if and only if, you'll see that you'll get the statement is always true. So, and it's a tautology because these two statements were logically equivalent. So a tautology is when the truth table has only true values, always evaluates as true. And I should point out here are three of our important logical equivalents. The first one we already talked about is how to distribute the negation across an and. You distribute the negation, but then you have to flip the and to an or. Similarly, to distribute the negation across an or, you distribute the negation, but you have to flip the or to an and. And then how do you negate an implication? You take P, but you and it with not Q. So these are three important logical equivalences that you should know. It should be in your back pocket. And we will have a few more things to say about this after we finish this example. And our next example is to use these logical equivalents to write the negation of these three statements. I am going to encourage you to pause the video and give these a try. But when you give these a try, make sure you are writing these as logical statements with P's and Q's and the implications, the ands and ors, and then use these logical equivalences when you negate. And especially this first one, it's very intuitive, and you can do this in an intuitive way, but you need to get used to doing this in a very formal way, because later you'll have more complicated things like the second one where your intuition may not be what you can depend on. So you need to be able to do this in a very formal way and using these logical equivalences. So the first statement, 7 is prime, or 2 plus 2 is equal to 4. So here I have P is 7 is prime, Q is 2 plus 2 equals 4. So our statement is P or Q, and we want to negate that. And we negate that using this rule. We distribute the negation, but then we have to flip the or to an and. And what we get is 7 is not prime, and 2 plus 2 is not equal to 4. Our next example, if M is bounded, then M is compact. So I take P as M is bounded, then M is compact, and my statement is P implies Q, and I want to negate that. So to negate that, that's this logical equivalence here, that's P and not Q. So I have P, which is M is bounded, and then not Q, and not Q. So and M is not compact. And our last example, if roses are red and violets are blue, then I love you. So P is roses are red, Q are violets are blue, and I love you is R. So this statement here is interpreted P and Q implies R. And we want to negate that. To negate the implication, we take the antecedent, which is P and Q, and then we and it with the negation of the consequent, so that's not R. So we have roses are red and violets are blue, but I don't love you. So that's the statement here. Before we go on, the first thing I want to point out is the importance of these logical equivalents, in addition to simplifying expressions, is being able to correctly negate compound statements. And the reason that is later you'll be doing proofs, and you want to be able to know when a condition has not been met. So a condition not being met is to look at the conditions and then negate and say, oh, these conditions haven't been met. So you're basically negating these statements. So that's why these are important. They will become, it's important you understand how to negate the, especially the consequent, to do proofs. Now, before we go on, I also want to talk about, I said I would talk a little more about the negation of the and negation of the or. And I'm going to do that with an example. My example is, if you attend class and you do the homework, you will get a passing grade. So I can write this out as P is you attend class, Q you do your homework, R you get a passing grade. So my logical statement is you attend class and you do homework, then you'll get a passing grade. It is very important to notice that the negation of P and Q, in other words, these are the conditions that you will get a passing grade. So the negation of this is not P and not Q. That would be dangerous, because then you might think, oh, the only way that you could fail these conditions is if you both don't attend class and don't do your homework. But the proper negation is that you haven't met the conditions of getting a passing grade if you don't attend class, or if you don't do your homework. So either of these conditions will not earn you a passing grade. Now that we have covered the first 4 topics, logical statements and connectors, logical implications, truth tables, and tautologies, we are going to save the last 2 topics, quantifiers and negation of quantifiers, for a part 2 video. For review, I have these 2 problems here. These last ones are after you've done part 2 of the video. Pause the video, give them a try, and then come back and there will be solutions. Here are the solutions. That is it for this video. Don't forget, part 2, we will cover quantifiers and negation of quantifiers. Thank you for watching.